Hi, my name is Sergey Levine, and today I'm going to talk about a general-purpose robotic navigation model. I'll describe some recent work we've done on robotic navigation and talk about some of its implications for interesting future research directions in robotics. First, let's start with some bigger picture points. If we go back about a decade in AI research, generally the way that we would approach building a model for a particular task, like for example image segmentation, is that we would collect a large labeled dataset for that task, and then we would train a dedicated model for that task specifically. And we would collect separate datasets and train separate models for segmentation, classification, image captioning, visual question answering. And the same thing held for other modalities, so if you want to do sentiment analysis or document summarization, in each case you would need to collect a fairly large, strongly labeled dataset and train a dedicated model for that particular task. And the transformation that we've seen in recent years is that now, increasingly, if we want to train models for these kinds of perception, classification, or generation problems, we would typically start with a large and unlabeled or weakly labeled dataset, which we would then use to train some kind of giant unsupervised or self-supervised pre-trained model, what some people call a foundation model. This could be, for example, a large language model, a masked transformer model like BERT, or a self-supervised feature extractor like SimClear. And then we would use this model to initialize training for whatever our downstream task is, where we would use a smaller or medium-sized labeled dataset, or keep the same large dataset and get better performance by means of fine-tuning, or sometimes even in zero-shot or few-shot prompting. And then we'd get a model for our task at hand. We've seen a lot of this consolidation within each modality, for example, general pre-trained representations for vision, or general pre-trained language models for NLP. Increasingly, we're also seeing consolidation actually across modalities, where we're seeing models that incorporate, for example, both text and images with the same kind of weakly labeled pre-training that can then accommodate a wider variety of downstream tasks. This is an example of a paper called POEM-E that I was involved in, where the aim was to get a language model to be able to take in multimodal tokens representing images. Of course, the big benefit of this kind of consolidation is that these large models can use much larger datasets than what would be available to each task individually. And that, of course, allows us to bring to bear the full power of high-capacity neural network models. So the question I want to discuss in this talk is, what would a general-purpose robotic navigation model look like? If we want to see the same kind of consolidation in robotics, what are the things we need to do to get there? You could call this a navigational foundation model, a navigation backbone, a pre-trained navigation model. You can also just call it a really great navigation model. Whatever you want to call it, the aim is to do for robotic navigation what BERT and GPT did for language, and what CLIP does for vision, and so on. So we'd want to take a large and very heterogeneous data set of previous experience of robots navigating various environments, train a very general navigational model out of this, which would understand obstacles, understand navigational affordances, and of course generalize across different kinds of navigating robots, and be applicable to various tasks. And then adapt this to some downstream task with a little bit of fine-tuning to enable things like, for example, autonomous driving, lane following, and things like that. So that's the vision. That's where we want to go. And there are, of course, a number of difficult problems we have to address before we can get there. Broadly speaking, the challenges involve developing algorithms for training these models, collecting and assembling large robot datasets that include the range of platforms, applications, and scenarios that would enable such a model to generalize broadly, and of course designing flexible and general models that are not only able to absorb a lot of the knowledge in the data, but can also be adapted flexibly to a wide variety of downstream applications. Remember, the aim is not to get these models to solve every possible task in zero shot, but to provide a very general purpose initialization that can enable downstream tasks to be solved efficiently. So I'll talk about each of these three pillars, but I'll start by talking about the algorithms. So to talk about algorithms, we have to ask, what is it that we actually want to learn? What objective can we use to learn general navigational common sense from diverse data sources? That is to say, when we take these large heterogeneous data sets from lots of different robots, and we plug them into some kind of box, that box is going to produce something which can then be adapted to driving off-road ATVs and controlling legged robots and so on. What does this box need to be? What does it need to do to provide initialization that could adapt in this way? Well, to start thinking about this question, we can first look at how unsupervised and self-supervised learning works in other domains. For example, BERT is an NLP model that can readily be fine-tuned to a wide variety of NLP tasks, And BERT trains by masking out tokens in sentences and then predicting the masked out tokens. So it fills in the missing tokens. Large language models typically do something very similar, except that they predict the tokens autoregressively. They predict the next token given the previous ones. Computer vision representation learning methods like SimClear, they predict representations of images after they've undergone some transformation. So they predict representations of cropped or transformed images. In all these cases, all these methods are essentially removing some piece of the data and then filling it back in again. So BERT removes a token in the middle and then fills it back in. Language models remove the next token and then fill it back in. SimClear transforms the image and then predicts the transformation. So it applies some kind of distortion and then figures out how to undo that. So all these methods, in a sense, fill in the blanks. They train on incomplete data. So we can apply the same idea to navigation. We can say, well, let's take all of our navigation data, remove some piece of it, and then try to train the model to fill it back in. Now, this is, of course, great because it doesn't require strong supervision. It doesn't require classes, labels, etc., and therefore can use all of the available data. So how can we do this with navigation? Which bit of data can we fill in such that prediction is not too hard, yet forces the model to learn useful stuff? Now, we could remove parts of the actual navigational trajectories, like the images themselves, and try to fill those in. That's a little tricky because that requires us to generate images, which is possible, but it has a lot of extraneous things. Like, for example, being able to generate the color of the walls is probably not the most crucial thing for learning navigational affordances. So here's what we could do. We can condition the model on the current observation and a little history. So you need that history to figure out what's going on in the world, and some future observation that you saw in that trajectory, which we're going to treat as a goal. So we're going to say that the robot, if it 10 seconds later reached some position and saw some image, it was intending to do that. Now, that's an assumption. That assumption is not always true, but it's reasonable to get us started. And then based on these things, the current history of observations and some future observation representing a goal, we're going to predict the current action the robot should take and the number of time steps between the current observation and the goal observation, what we can call a dynamical distance or temporal distance. Now, why are we predicting these two things? Well, predicting the action will force the model to learn about local navigational affordances. It'll force it to figure out that if you saw certain things and then you reach certain things in the future, these are the actions you should take now to get there. That's very useful local knowledge. The temporal distance allows the model to learn global knowledge. It allows it to figure out roughly how connected things are in the world. And this is really important because ultimately, if we want to solve long horizon navigation problems, we're going to need to figure out global connectivity. And that global connectivity will require understanding how reachable certain things are from other places. If you're familiar with reinforcement learning, you'll probably also recognize that these temporal distances are very closely related to value functions. So these prediction problems, in a sense, map very readily onto actor-critic algorithms, where learning to predict the action essentially represents the actor, and learning to predict the temporal distance essentially represents the critic. And in fact, when we use these kinds of models for online reinforcement learning fine-tuning, we'll actually build directly on this intuition. But for now, this is basically the setup. It's a very general objective. You can use any navigational data, because as long as you can pull out actions, you can address these kind of prediction problems. If you don't have actions, you can use structure from motion to figure out ego motion and turn that ego motion into actions. In fact, the action representation we use for all of our robots is ego motion. So if the robot is controlled with steering and gas, we would just integrate those forward to get ego motion on some short time scale. This prediction problem captures collision avoidance and basic navigational common sense, because you'll never actually see actions that don't lead to the future observation, because, well, that's how the actions were obtained. You take the trajectory, take a future observation, pull out the action that led there, so the action always leads to that future observation. You'll never see physically impossible things, which means that you'll learn about things that are physically possible. And it's actually directly useful for zero-shot navigation. So while our aim ultimately is to use this objective to pre-train a general model that can then be adapted to a variety of downstream tasks, straight out of the box, this model can be prompted with a goal image, and it can, in zero-shot, attempt to navigate to that goal image. So let me tell you about a little bit of work that we've done over the past few years to set up models that can be trained with these objectives. Now, many of these models are not yet aimed at the kind of flexibility that we would like from a true navigational foundation model, that I'll talk about a little bit later, but they illustrate how this very general pre-training objective can be used effectively to enable some capabilities and also to absorb very large sources of data. So the first project that we did studying this for navigation was in 2020. It was called ViKING, led by Drew Shaw, as well as a few other students, Benjamin Eisenbach, Gregory Kahn, as well as Nick Reinhardt, who was a postdoc at the time. And the aim there was really to just build one of these models to enable robots to navigate to visually indicated goals. So here, a user takes some photographs of their front door, and the robot is supposed to deliver the mail to their front door using one of these image goal condition policies. So the problem setting is find and navigate to a given goal landmark using only camera observations. The robot gets its current observation, it gets a picture of the desired goal, and it's supposed to figure out what to do in between to solve the navigational problem. In a lot of these presentations, I'll show some overhead views. Unless I state otherwise, the overhead views are provided for your illustration, although in some cases we will actually give satellite images to the robot to aid in navigation, but for now we're not doing that. So the model here is very straightforward, exactly as I said before. The robot receives its current observation, it receives a goal observation, which is only a short distance into the future. Imagine, let's say, something that the robot can roughly see from its current position. And then the model predicts the number of time steps between the start and goal in the training data, as well as the current action taken at the current image. Now, this only provides us with short horizon navigational capability. If we want to enable the robot to navigate further away, what we do is we employ topological map. So the idea is that whatever other experience we've had in this environment, we take all of the images that the robot has seen, and those correspond to nodes in a graph. And the edges in the graph are formed by using our model to predict the distance between those pairs of images. Now remember that the distance here corresponds to the model's estimate of how many time steps it would take the robot to drive from one observation to the other. So that's a very natural measure of connectivity. And now you can hopefully start to see why predicting these temporal distances is so useful. So if we previously have some experience in a given environment, we can take all of the images, connect them up into a graph, and then if we want to reach a very far away goal where the model would not be able to provide the right action in zero shot, what we would do is we would plan through this graph, connect the current image to the graph, connect the goal image to the graph, figure out the path, and then drive to the first waypoint. Interestingly, the training of our initial model for this didn't actually involve collecting any new data. We actually directly reused data from a previous project that Gregory Kahn carried out on a very different system. That was about 40 hours of navigational data with this Jackal robot, and it turns out that that was enough to train this fairly general goal and distance prediction model. And this system could do some rudimentary things like drive to those doors to deliver mail that I showed before. But of course, it required the environment to have previously been visited by the robot so that we had a graph. If we want to build a graph on the fly, what we can do is we can use autonomous exploration, where the robot actually constructs the graph as it goes, and employ some heuristics to bias it in the direction of the goal. And that's what we explored in this next project called ViKING. So here we are actually going to use those overhead views. So the idea in ViKING is that we'll have the same kind of model that will predict the distance to the goal, the action. It'll also predict a spatial GPS offset, which we will use to index into an overhead map, basically a satellite image or a road map from Google Maps. And that'll be used to employ kind of a heuristic search. Think essentially like A-star search, but in the physical world. So there's a separate heuristic model that looks at the overhead map, that looks at the satellite image, and it basically predicts, given the current position and the goal position, and some intermediate position that we're considering as the next waypoint to explore, what's our guess as to whether that's a good waypoint to explore or not? And that's learned with a contrastive learning method. So the full ViKING method uses a latent representation of waypoints to sample potential waypoints that the robot could visit, employs this model, this goal condition model, to compute edge distances, employs the heuristic model to compute heuristics, and then basically employs a kind of a physical analog of A-star search to find a path to the goal. And this ends up working really well for very long horizon navigational problems. So here we're placing the robot in this environment. It's a kind of it's Richmond Field Station up north from UC Berkeley. It has not mapped out this environment before, so this is the first time it's been placed in this test setting. It is given a satellite image and the GPS coordinate of the goal, as well as the goal image. And what it's going to do is it's going to perform this incremental graph construction while it navigates to the goal. Now, in many cases, the heuristic alone predicts reasonable paths by telling it to basically follow the roads. Sometimes it cuts across the grass. But the heuristic, of course, is far from perfect. It is just a heuristic after all. So sometimes the robot will enter some dead ends. So here you'll see in a second, it'll drive into this parking lot. Now the parking lot is actually a dead end, but once it realizes that it's a dead end, it just backs right out, goes back on the road, and navigates to the goal successfully. So this is really the benefit of using graph search in combination with these heuristics. Viking can navigate to goals that are over a kilometer away. If we give it some intermediate checkpoints, it can follow a hiking trail that's almost 3 kilometers long. It doesn't rely on the satellite image being perfect. So here, a semi-truck was placed in an opening in the top right that prevents the path that looks open on the satellite image to be viable for the robot, and it automatically reroutes around it because it's only using those satellite images as heuristic. If we give it no satellite image but only GPS, that's the pink line, it can still reach the goal, although of course it makes more wrong turns and hits more dead ends, but because it's replanning using this graph, it's still able to succeed. In fact, it can even explore an environment without GPS at all, that's the cyan line, although of course when the goal is far away, it will eventually get stuck, and the further the goal is, the less likely it is to reach it. Now this is really promising because it illustrates part of the generality of these kind of goal condition policies, that if we can build goal condition policies like this, then we can employ them to solve very complex navigational problems. But of course, this work is still operating at the level of one robot and in a particular range of environments, in these cases outdoor environments. So it's not a true navigational foundation model yet. To further illustrate the flexibility of this idea, though, let me tell you about another project that we did that uses the same kind of model in a different way. In fact, for this project, we actually didn't train any new models at all. We basically showed how these goal condition models could be combined with large language models to obtain a system for following language instructions without any further training. So in this case, we're going to take an instruction like after passing a white building, take a right at the white truck. We're going to pass that instruction through a large language model to pull out the individual landmarks that the user would like you to visit, like the white building and the white truck. Then we'll match up those landmarks to images that we've seen in the environment, to nodes in our graph essentially, and that'll be done using a vision language model like CLIP. This will give us a score for visiting certain nodes in the graph, and then when we plan, we'll modify our planner so that we maximize the probability of visiting all of those nodes, which in turn will maximize the probability that we actually follow the instruction successfully. We call this LM-Nav, navigation with language models. When this work came out, this was actually one of the first works that used large language models for navigation. And the steps are pretty simple. Construct the graph using the visual navigation model from before, like exactly this Viking model. Extract the landmarks using a language model. Attach those landmarks to nodes in the graph using a vision language model like CLIP. And then perform a graph search that takes into account the probability of visiting the landmarks in the order specified in the language instruction and in a way that leads to a short and successful path. And then we can do things like get an instruction for the user. The instruction might say, for example, go straight towards the white building, continue straight passing the truck, or it might say, take a right next to the stop sign, look for a glass building after passing a white car, and the robot goes off using the graph to figure out where to go. And here you'll see that it navigates, figures out, okay, there's the stop sign, done with the stop sign. Next, go to the white car, because it says glass building after passing a white car. The language model can figure out that the white car comes next. So it goes and finds the white car. Takes a little while to get there. It's a long drive. But there's the white car. It sees the white car, and now it's going to go to the glass building. And now it's done. Now it's succeeded with the task. Okay, so that was a discussion of algorithms. But now let's try to scale this up. And to scale this up, let's talk about data sets. So far we've been controlling a single robot in these kind of outdoor environments. But what if we want one policy to control many robots in a wide range of different environments? Well, what we can do is we can pilfer all sorts of data sources from the web, from other people's research projects, or maybe contact them directly to see if they'll donate their data to us graciously. And that's exactly what we did. We assembled a data set with 6 different robots, 8 different data sets. That includes everything ranging in size from large-scale ATVs to small-scale RC cars to legged spot robots. And then we applied all of this data to train a model more or less along the same lines as the model that I described before. The only real difference is that now, besides the model being bigger, it's provided with a little temporal context. So it's not just provided with a current observation, it's actually given a little history of past observations that it can use to try to figure out what kind of robot it's controlling. We thought about giving the model richer representations of the robot that it's controlling now, like, for example, some parameters, maximum speed, etc. But we actually found that just this temporal context was actually often enough to get the model to drive a new robot successfully. In fact, the model generalized so well across robots that it could control new morphologies in zero shot. For example, it could fly this drone shown in the top left in this animation without ever having been trained on drones before. The drone here is pretending to be a car in the sense that it's flying at a fixed altitude, but besides that, it is quite different. It has different cameras, different dynamics, but the model is still able to control it. There's some pretty nice effects that we can get once we train this very large multi-platform model. The model can control many different kinds of robots. It can control them indoors and outdoors, in the day and at night in a wide variety of settings, different buildings, different outdoor environments. The model also becomes more robust. So by training on many different robots, it can generalize to settings where maybe one of the robots was modified. So here we took a robot that was in the training data, the Jackal robot, and we put a stick in the tire to simulate tire damage. Now, in this case, the tire damage really does change the dynamics of the robot. If we use a single robot model and just tell it to drive the robot straight, after the damage, the robot veers off to the side. So it's very hard to control it after this damage. But if we use the GNM, which was in fact trained to control a variety of robots, then it can actually control the robot both before and after the damage, because essentially the damaged robot is just another kind of robot. If you generalize across robots, then you can generalize to this kind of stuff. Here's the video with the drone again. Now, as I mentioned again, the drone is flying at a fixed altitude, but you can see that it has a pretty different fisheye camera, and yet it's able to successfully navigate this hallway. We can also use this model to initialize online RL, and this is one of the more interesting things that we did recently. So here the idea is that we do offline RL pre-training to learn, to basically treating these distances as a critic, and we use IQL for offline RL pre-training, and that we do on the entire data set, and then we do online fine-tuning. Online fine-tuning is done with RLPD, a sample-efficient online algorithm. Now, 5 minutes into training, you can see that the robot is supposed to race around this building, race around the circuit of fifth floor sort of hall, and you can see 5 minutes in, it's not doing a great job. It is making some progress around the track, but it's bumping into things a lot. So this is 5 minutes into training. Now, this is much better than what we would do if we just started off with completely random actions, but of course, still not great. But then if we move forward 10 minutes, it's going to get quite a bit better. So here's 15 minutes in. You can see at this point, the robot, still not perfect, still hits the wall a little bit, but it's pretty consistently making progress. And it actually learns to accelerate a little bit on the straightaways, although some of the turns still give it a little bit of trouble. And now, if we go 25 minutes in, at this point, the robot is pretty consistently able to make it all the way around the circuit. It's actually able to drive pretty fast, and it knows to accelerate on straightaways, slow down a little bit on the turns to make sure it doesn't hit the wall. And at this point, the robot actually drives at speeds that are comparable to what the expert human driver, the graduate student who was doing this research, Kyle, was able to do from the same first-person camera. If the graduate student can use the third-person view, if the human expert can use the third-person view, they can go a little faster. But from the first-person view, the policy is at about human level. They can also work outdoors. So 5 minutes in, this is the outdoor racing. It's supposed to go around this building. You can see it's not great. It still hits the building sometimes, but it's more or less going in the right direction most of the time. This is, I believe, about 20 minutes in. And at this point, it can pretty consistently make it around the building, and it knows that if it goes on this little path, it can go a little faster. Now, it has checkpoints that it has to go through that are off the path, so it has to go on the grass. But in between those checkpoints, it tries to make a point to get back onto the path so it can drive a little faster. Now, it's worth noting that these policies control the robot directly from raw image pixels, and they're learned in 15 to 25 minutes. This is extremely fast for image-based RL directly in the real world. Now, of course, this is an illustration of just how much that pre-training helps. The pre-training basically already gives the robot basic navigational affordances, and mostly what it has to do is adapt those affordances to this robot type and to this particular racing circuit. And remember that the pre-training doesn't get any data from this robot at all. It only gets data from other robots driving at much lower speeds. Here's the first-person view of the outdoor racing, and you can see that it's, given the small size of the robot, the bumpy ground actually gives it quite a lot of trouble. So the physics of this kind of driving are actually quite complex. It's definitely not as simple as just going from point A to point B. Okay, so we showed some generalization across robots, but the models so far have not been huge. There's still convolutional neural networks that are maybe kind of at the scale of what we would expect maybe 5 years ago. Of course, these days, large transformer-based models have enabled much broader generalization. So the next obvious thing for us to explore is, can we take this recipe, these self-supervised algorithms with these large data sets, and scale them up to much larger models? And that's what we did in our most recent work that we call ViNT, the Visual Navigation Transformer, where we used a similar setup to the GNM, but we used a large transformer model with 30 million parameters to train a model that can not only control many different kinds of robots, but also provides us with more flexibility in how it can be adapted to a variety of downstream tasks. So the ViNT transformer, which outputs a tokenization of actions and uses tokenized images, uses training data from a wide variety of robots, and it can be used for zero-shot navigation, both in seen and unseen environments, and it can be adapted to a variety of other problems. So let me first talk about how we can adapt ViNT to explore a new environment. So the problem, of course, is that ViNT requires goal images to be given to it, but if we're in a new environment, how do we pick which goal to provide so it will explore the environment? It turns out that a very simple solution worked really well for us. We simply train a diffusion model to predict possible images that can follow the current observation some number of time steps into the future, and then we sample from that diffusion model to essentially specify exploratory goals. Now, as you can see on the right, many of the samples from this diffusion model are not very good in the sense that they don't actually look like plausible images the robot could reach. Some of them are good, but some of them aren't. But ViNT is such a powerful model that when it's provided with a goal image that is not feasible, it simply defaults to some kind of reasonable collision-free navigation. And when it is provided with a reasonable sub-goal, then it follows it, and that drives exploration. And we found in practice that even with random images, ViNT would perform collision-free navigation in new environments, but when it's provided samples from this diffusion model, then it achieves much better coverage. It can often discover goals even in environments that it hasn't seen before. So here's a video of ViNT navigating to a desired position in a previously unseen environment. And here we have two videos where it starts in the same place in both cases, but it's given two different goals. And you can see that it explores the hallways and eventually reaches those goals. And you can see that in both cases it actually experiences no collisions while doing this. We can also use ViNT in kind of unstructured exploration or mapping mode. So we can simply put it in a new environment and not give it a goal at all. We can also use it in a much more structured way. So here we actually give it a satellite image and employ that same heuristic from VIKING. And for this outdoor setting, the satellite image here is actually a road graph. It actually figures out how to navigate this environment, go through a parking lot, and reach this faraway goal that's about 800 meters away. So that's pretty cool, kind of similar functionality as VIKING, although it generalizes quite a bit better in this case. And here's the unguided version. So here, it's not provided with a goal at all. It's simply sampling candidate goals from this diffusion model and exploring the environment to see if it can achieve good coverage. And you can see that it definitely exhibits basic things like collision avoidance. This is not an environment that it was trained in, so it's generalizing to this in zero shot. And we can generalize to new robots, and as well as to some degree to dynamic obstacles. So there were no dynamic obstacles in the training data that we know of, but here, some people walking, we instructed them specifically not to change the direction of walking in response to the robot, but the robot does a little turn to kind of get around them. So that's a good sanity check that it does have some emergent capability to a degree to handle dynamic obstacles. And here's an unseen robot, a Go1 quadruped. This quadruped was not in the training data, and you can see that the policy in zero shot can control it to explore this environment without collisions. Now, not all tasks can be specified with goals. So one of the nice things about using these kinds of transformer models in ViNT is that we can employ methods similar to prompt tuning to adapt ViNT to new kinds of problem specifications. So let's say that we want a task that is not specified as a goal. What we can do is we simply replace the goal encoder with an encoder for some different modality. Maybe our modality now is to follow turn-by-turn instructions like turn left and turn right. We'll train a separate encoder that encodes those instructions into the same tokenization as the goals used by ViNT. And this can be done with a small to medium amount of data, and then we can follow different kinds of task representations. And we can do this with a pre-trained ViNT model. So we experimented with this by replacing the image goal token with GPS coordinates. We can also replace them with routing commands like left, right, and straight. The basic ViNT backbone is pre-trained, and then the encoder is retrained from scratch for the new modality. So here's an example of transferring ViNT to drive in Carla, where the commands correspond to left, right, or straight. And you can see that here the Carla video, which unfortunately is not playing, would show the robot driving around in this environment. Okay, here's the Carla video for your reference. So you can see here that the robot correctly follows the navigational instructions and can follow lanes. So some takeaways and perspectives about ViNT. The goal here was really to do for navigation what BERT and GPT do for language, or what CLIP does for vision. There are still quite a few questions that are left unanswered with this method. For example, different navigational contexts have different rules and conventions, like sidewalk driving versus driving on the road for an autonomous car. The model doesn't really have any way to take into account things like rules of the road, although it is fine-tuned with some amount of data, so the fine-tuning itself could imbue it with some amount of those rules, but it would be interesting to explore other ways to give it more context, like language descriptions. So more complex prompting could make the model significantly more flexible. And potentially, we could generalize to platforms of very different capabilities if we provide a richer context into the model. So maybe we could control a drone with control of its altitude if we have a variety of different action spaces. Now, these are all really exciting things to explore in the future, but I do think that the current results for ViNT indicate that it's quite possible to build a very flexible navigational model for many, many different settings. I also think that one of the most interesting things about ViNT is the capacity to adapt to other task specifications with things like these prompt tuning methods, which really starts to have some of the same kinds of applications as the foundation models we've seen in other domains. Okay, but at the end of this talk, I want to leave off with a little bit of broader philosophy. So far I've talked about robotic navigation at length, but there's a lot more to these kinds of problems, I think, than just navigation. And to get into this philosophy, I want to talk about a much bigger question. And that bigger question is, why do we need machine learning? And to start answering that question, I think we can ask an even more basic question. Why do we need brains? That might seem like kind of a strange question to ask, but there's an interesting answer that was offered by Daniel Wolpert, who's a neuroscientist that studies motor control. Wolpert said, we have a brain for one reason and one reason only, and that's to produce adaptable and complex movements. Movement is the only way we have of affecting the world around us. I believe that to understand movement is to understand the whole brain. Now, this may seem a little reductionist, but I think this is a very valid point. Essentially, the brain is there to move your body. In that same way, machine learning is arguably there to produce adaptable and complex decisions, in the sense that, in the end, the value of a machine learning system is in the decisions it makes. This perspective might seem obvious, but I think it has some non-trivial implications. Of course, if we're talking about controlling a robot or driving a car, the decisions are obvious. But if we're building, let's say, a computer vision system, that is also a system that makes decisions. Those decisions are not necessarily the labels. They might be the consequence of those labels. For example, if you are detecting people with a security camera, the decision is, do you call the police or something like that, or do you raise the alarm? If you're detecting, for example, objects in satellite images, the decision might be to notify a human operator that you found something interesting. These are decisions that lead to downstream consequences, and methods that can reason about decisions and their outcomes could in principle be better methods for solving a lot of machine learning problems. So what does this have to do with robotic foundation models? Well, perhaps the real value of robotic foundation models is to give us a way to train general models that are just really good at making decisions. See, a lot of the pre-training methods that we use for foundation models in other domains, like computer vision, don't train the models to make decisions. Pre-training with SimClear is not training a model to make decisions, it's training it to figure out the effect of data augmentation. BERT is not training the model to make decisions, it's training it to fill in missing words. LLMs are sort of training it to make decisions, but the decisions aren't necessarily good, it's just training it to copy text from the internet. But pre-trained models that directly take meaningful and useful decisions, that could be really useful, because if all of the downstream machine learning tasks are at the end of the day decision-making tasks, then perhaps pre-training for decision-making in the way that these general-purpose navigation models are trained could really be the key to making machine learning much more powerful. And perhaps this idea extends far beyond robotics. So maybe we can generalize this idea that if we have a big data set from past interactions, past tasks that the robot has done, past tasks from videos from the web, and other sources of information that we can use to figure out decisions and their outcomes, and we use this to train a large model with offline RL or offline goal conditioned learning or some other kind of decision-centric objective, and there we have a variety of different choices, then perhaps we'll acquire a general representation that can be suitable for learning a downstream task that is particularly attuned to making decisions and reasoning about their consequences. And if we need machine learning for one reason and one reason only, to produce adaptable and complex decisions, this kind of decision-centric pre-training could be very powerful, not just for robotics, but far beyond that. So perhaps building robotic foundation models will help us build much more powerful self-supervised pre-training methods more generally. I'll leave off on that point and thank the students who carried out this work, particularly Dhruv Shah, who's been the leading student in a lot of the navigational work, together with colleagues Kyle, Ajay, and many others. Thank you very much for listening.